Hello everyone, this is Mushfiqur Rashid Khan from INP BUET presenting the basic contents of our accepted research work titled An Ensemble Learning Classifier to Predict Net Electricity Generation from Nuclear Power Plants. This is the overview of the presentation and these contents will be discussed during the whole presentation. These are the acronyms which will be discussed in the whole presentation. Nuclear power plants supply the generated electricity available for transmission and distribution to the power grid, which in turn powers residences, commercial establishments, and other electrical consumers. It is essential to make appropriate predictions about the electricity generations to avoid the system losses, and it is a crucial statistic for assessing the capability and performance of nuclear power plant in terms of its real contribution to the generation of electricity. There are some significances of the prediction of net electricity generation. Forecasting electricity generation enables efficient energy trading and market operations, enhancing resource allocation and decision making. It encourages economic efficiency and cost saving by enabling market players to make well informed decisions about electricity purchases and sales. Without the capacity to forecast electricity generation from a power plant, system failure can have a big socio-economic impact. Inefficient electricity transmission and distribution can lead to system losses, which raise electricity prices. There are some factors involved in electricity generation using NPPs. They are how well the nuclear reactor converts the energy generated during nuclear fission into electrical energy, how much power is actually produced compared to what might be produced if the plant ran continuously at full capacity, and the most importantly, the availability of an NPP is determined by the proportion of time it is able to generate energy. For this research, we have studied 23 relevant and recent research works, which includes the contents of renewable power generation prediction models in energy sectors and predicting electricity generation with machine learning. In this research, least cost forecasting models were created by reducing the RMSE, MAE, and MAP. The findings showed that the electric load prediction architecture based on support vector regression appears to be the most reliable architecture and can reduce 0.313 million Pakistani rupees daily. In this research, an electricity generation forecasting system was suggested that might anticipate the necessary electricity at a pace that is close to the United States electricity uh, consumption. The suggested system, trained for the prediction step using an ML model, can estimate the needed electricity generation at a level that is close to 99.9% of the actual use. After studying some relevant and recent research works, we have found some research gaps. A few research works are already done for electricity generation using different machine learning techniques in NPPs. Making a perfect prediction of net electricity generation is necessary using an ensemble learning classifier, and the most importantly, a time series data driven methodology using different ensemble learning classifiers are used in our research. After finding some research gaps, we have some motivations and purposes for this research. Inflection of AI has assisted particular programs to find patterns in huge datasets. A vast scope of ML models to improve the efficiency of ensemble learning classifiers, which is abbreviated as ELCs, for predictions and classifications in nuclear power plants. Our curiosity and interest have driven us to perform a proper prediction of net electricity generation using different ELCs to trace down the most efficient one. For this research, we have collected the dataset which contains 267 observations for the net electricity generation from nuclear power plants situated in the USA, which are from January 2001 to March 2023. This is a time series dataset and each sample is taken after 1 month. The net electricity generation is calculated in 1000 megawatt hour. This is the graphical representation of monthly electricity generation from NPPs in USA, and this is also the graphical representation of the monthly variation of electricity generation from NPP in USA. For this research, we have constructed a proper methodology First of all, we have collected the input data, and after that we have performed the data preparation for the further works. Uh, After the data preparation, we have used the ensemble learning classifiers to obtain the final outcome. The ensemble learning classifiers include random forest, voting ensemble, AdaBoost, and bagging. An adaptable supervised learning approach that is simple to utilize is random forest. Outliers, noisy data, and missing data can all be handled with it, which produces a precise forecast and useful insights into feature relevance by mixing numerous decision trees. This is the prediction approach of random forest classifier. A classification technique called voting ensemble combines the prediction of many distinct models to produce a single prediction. To better comprehend the data and the decision making process, it can offer insights into the consensus and divergence among the multiple models. This is the prediction strategy of voting ensemble classifier. A group of weak classifiers is formed by the classification algorithm AdaBoost, which improves the performance of ML algorithms by merging them into a strong classifier. And this is the classification strategy of AdaBoost classifier. Bagging classifier makes the use of the idea of ensemble learning to increase the prediction accuracy and decrease variances by training them on several bootstrap samples of the training data. Bagging combines numerous base models frequently decision trees to produce a powerful classifier. This is the prediction strategy of the bagging classifier. For the experiment, we used Python programming language and DeepNote IDE. And again, for the experimental setup, we used decision tree classifiers for the base classifier as the base classifier, and we used different number of estimators such as 100, 10, and 50 for random forest, bagging, and AdaBoost classifiers respectively. We used 42 random states, and we splitted the data into 70% training and 30% testing ratio. For this research, we used uh, four evaluation metrics such as accuracy, RMSE, MAP, and training time. And we used these types of formula for accuracy, RMSE, and MAP for the calculation of the obtained results. Using the experimental setup and the evaluation metrics, we have found the experimental results, which is shown in the graph. The graph exhibits that the random forest has the best accuracy score and a better performance than the other classifiers, considering the MAP and RMSE. The training time analysis uh, shows that the random forest has the least training time, uh, considering the other classifiers. We have compared our obtained result with the other existing works, and we can see that we have a better work than the other relevant works. After completing the whole research work, we have some novelties and impacts in this research. A pioneering endeavor for predicting net electricity generation on a monthly basis using an ensemble learning classifier is performed. This research will help engineers and power plant operators to operate nuclear power plants effectively to produce a sufficient amount of electricity in a particular month, which can make a significant contribution to preventing system loss, and it can have a social economic impact in a particular country. We have some limitations and future works in this research. A limited number of input data is utilized. The computational cost of training numerous models on a dataset containing a limited number of data points may exceed the advantages of ensemble approaches, and these problems can be solved later with more data and other ML approaches. The data is available in the following link. These are the reference papers of this research. That's all. Thank you.